Okay, so I want to explore this. Now, unfortunately, hindsight is 2020. I don't have these examples in the problem book. I'll just make them up to illustrate how 0 over 0 is an indeterminate form and can result in any answer. Okay, so let's look at some example. The first thing I do is look at the form. That's my choice. You don't have to, and no books will tell you to do that, but it's so convenient. How could I not when I know it works? Nothing else is going to be as fast as this. Still reliable. Now I look, what does the numerator do? It is going to 0. What does the denominator do? It's also going to 0. Okay, it's not the answer I was hoping for, or the form I was hoping for, but at least it tells me, okay, now go and look at this function and see if I can clean it up and look at a behavior of a simpler function that's equivalent. Okay, well, for rational functions, it's really about trying to factor this and see what I can do. So I factor it, and I see if I can do any cleanup here. Yeah, the x minus 2's cancel, and I can cancel them, still have an equal sign because I'm saying the behavior is equal, not the functions. If you don't have this limit in front and you write an equal, that's wrong because they're not the same function. The behavior of the original is the same as the behavior of this simpler rational function. It's simpler. So let's check the form of this guy. I have a new function in the limit question. So let's see if the form is the same or not. Numerator goes to 4. Denominator goes to 0. It's a new function. The form could change, which is why I do it again. It's 4 over 0. Now that is a much more telling form. It says the numerator stays constant. Well, it's not constant. It's going to a constant 4, where at the same time, the denominator shrinks to 0. How does the whole thing, the whole fraction behave? The size is going to do what of the whole thing? When I have a top that is constant to a non-zero number, the bottom shrinks down to 0. Plug in some numbers. 4 over, I know it's not exactly 4, but it's pretty much 4. 4 over 0.1. 4 over 0.01. 4 over 0.001. What happens to the whole thing? It was up here somewhere. It's the same as this guy. Yeah, same as this guy. It blows up. It gets bigger. Now, sometimes I will say it depends on other things, that this could be a positive or negative infinity. I don't want to necessarily commit right now. The point is the size blows up. I don't want to get caught up. Sometimes it's not obvious. Yes, the size blows up, but is it always positive, always negative? I don't know, but I do know the limit doesn't exist. I'll tell you why in a second. Limit does not exist. Because if I look at this 4 is always going to be positive, right? This 4 is always going to be positive here. But as I am interested in the x equal 2 position, I'm coming towards 2 from either side. I always have a window around 2. So if I'm on the right, then I have a bigger number minus 2 being positive. The whole thing is positive. But if I'm on the other side of 2, then I still get a number really close to 0, but it's always negative, a smaller number minus 2. So depending on which side I come at it, I could have negative or positive numbers. And I don't want to make a big deal of this now when it's going to come up later in a way I can handle much more easily. So if you just put n infinity there, doesn't really matter which one. But if I'm not sure, put a plus or minus. It's all good. It's all good. We don't have all the tools ready to really easily pick out which one. Later on, it's going to become quite straightforward to know which one it is. I don't want to get distracted with that when it sort of takes away from our focus right now. Later on, it's going to be very straightforward to do. And then I might want to know, because I want to graph it. I want to know, does it go up? Does it go down as I get close here? I want to know which one. Yes, okay, sure. Then we have to really figure it out. Right now, I just want to know about the size. Okay, the size gets bigger. Okay, so I can have a 0 over 0 form originally resulting in an infinity and a limit that doesn't exist. All right, it's good to know. Let's see something else. So on a test, would we put plus and minus infinity? For this kind of question, I'm going to accept any sort of infinity here. I don't really care. It's a question of general size behavior, to be honest. Later on, when we want to graph this function, and one of the questions will be this question, what happens at 2? Then I need to know, because I want the graph to be correct. That's a different question. So any infinity you put there, it has to be an infinity though. Because I understand that our tools aren't our toolbox isn't complete. We can't easily find that infinity every time, so don't worry about it. That's not the goal here, to be honest. The goal is what happens to the size of the y value. Let's look at a very similar one. 2. I'm going to flip them around. It's not very original, I know, I apologize, but it gets the job done. First thing I do, I look at the form. That's literally the first thing I do. And I see, oh, the top 0 goes to 0. The bottom wants to go to 0 as well. Indeterminate form, don't know exactly what the answer is going to be right away, which means I go back to my function, look, what kind of function do I have? Oh, I have a rational function. Let's try and factor this and see if things cancel and good things happen. I have, of course, the 2x minus 2's at the top. I have the difference of squares at the bottom. So now, because I'm only asking for behavior, I can say the behavior of the original is the same as the behavior of the simplified version, even though the function itself is not the same. That almost looks like a 3. I'm talking about behavior, and the behavior is the same. As a new limit, essentially, so I can look to see if the form is changed. Top one goes to 0, bottom one goes to 4. Wow, that is very informative. I now have a denominator that stays constant or approaches stability at a non-zero number. The numerator, in the meantime, shrinks down to something super small. What happens to the whole fraction? And if you don't know, totally fine. Plug in some numbers. 0.01 over 4. 0.001 over 4. 0.0001 over 4. It's going to shrink down to 0. Does this limit exist? Yes or no? Because you'd be surprised. Getting an answer of 0 is maybe something people can do, but they don't associate 0 with a limit existing. That's a number. 0 is a number. Don't discriminate against 0. It's a number. Yes, it's very special. It's just a number. Limit exists. So having a 0, form originally, being able to cancel out that denominator problem, making the denominator 0, means I have this whole issue again, which is a minor technicality, really. But I don't necessarily know that because I don't want to graph this. I don't know what the graph looks like. I gave you the graph. No, not there. I gave you the graph there. In general, I don't know what this graph looks like. Behind the scenes, when I have a 0 over 0 form that I can sort of get rid of, it shows that at the y value of 0, there's just a little hole there. Nothing major happened. Nothing to be concerned with. All right, big smiley face. I'm going to take that as a good sign. So we see that 0 over 0 can result in different answers, which is why it's called an indeterminate form, because we can't determine the answer just from the form alone. How did we get 0 over 4? You see what happens to just the numerator when x goes to 2. Well, the numerator is x minus 2. 2 minus 2, 0. So the numerator alone wants to go to 0. The denominator is x plus 2. Close to 2, it wants to go closer and closer to 4. 2 plus 2. So now I have an interaction of a numerator and a denominator that does different things. The numerator, what it does is shrinks down to 0. Denominator, no, it's going to happily go to 4. Never going to be perfectly at 4, but they're going to be so close. And that numerator is going to force the whole fraction to shrink down. The denominator doesn't balance it and try and counter it and try and do anything. So the numerator determines what the whole fraction is then doing. But initially I couldn't see it. Initially, technically, the numerator and denominator both go to 0. And then it's a question of how do they interact? How fast do they go to 0? What other things are they doing? Well, it turns out the numerator goes to 0 much faster than the denominator, and the denominator can't keep up. But I can't see it in the original form. Okay, one more example. I look at the form of this limit because regardless, it's going to tell me something. I hope for a lot, but I'll take a little. When I plug in a 2 in the numerator, I get a 4 plus 2 is 6 minus 6, 0. And the bottom is also 0. So I can't say anything immediately. I need to go and look at the function, look at the specifics, and see if I can somehow clean it up, somehow clarify what's happening. And like in the rational function case, factoring, trying to cancel the denominator is often my best attempt. So can I factor the top? I hope I can. It's a plus 3 and a minus 2. Now please be aware that just because I have 0 over 0, just because I can factor the numerator doesn't mean I will always cancel something. Look at this first. Okay, the first one is a bad example. I still canceled something. I think we're going to get to something where it's not necessarily the case. And even if I can cancel something, I might not cancel out the problem, making this whole thing undefined. There's absolutely anything can happen. Maybe I'll do a little example. I might have. Let me just check. I'm going to do 17 and 18, and they might. I think they're going to show what I mean. So let's just wait for those. So now I see, ooh, yay. I can cancel the x minus 2s, and the x minus 2s were the problem. Well, there was only one in the bottom. So the behavior of this original function is the same as the behavior of x plus 3, which doesn't have any problem. It's a polynomial. It's great. Plug it in. It's defined everywhere. It's 5. 2 plus 3. I can look at the form here, but in the case of a continuous function, the form is exactly the same as just plugging it in. And it's a little unnecessary to double up with something that's overkill. Of course, limit exists. So, to sum up, in all these cases, I had 0 over 0. But literally anything can be the answer. And I don't know until I look at the specifics of the function. That is the lesson here. I'm always so close to banging my head against the table when I still see in tests someone gets 0/0 and then they say it's equal to 1. And I'm like, where were you for the last months? That that is not how things work at all. I am just trying to indicate how pieces behave relative to each other. Actually, no, individually, not relative to each other. And if I get a 0/0, well, that can mean many, many different things. Let's go back to our problems. We haven't done. These should be in the problem book, but they're not, so I still had to add them. Very important to see. But let's go something that is in the problem book, 3.2, number 17. Let's have a look. I don't want that. I want this. 17. Where are you? I guess I shouldn't scroll so fast. Slow it down. Slowly. Reveal 17. Boom, there it is. Okay, now I just copy that. Limit. Once we understand how to look at these things, I feel like I should apologize. There isn't really much mystery here, but we'll try and see if we can come up with some mystery. X squared minus 1 over x cubed minus x. Right? Yeah, pretty sure. Yeah, okay. Try and plug it in. It's not going to go well. Your calculator says error. So I now have to figure out where does that error come from? Why is this function not defined at 0? Could be a little hole, could be a vertical asymptote, could be, well, really, those two. So I get plugging in 0 at the top gives me -1. Plugging in 0 at the bottom gives me 0. What does this tell me? I claim it tells me everything. Well, enough. Almost everything. If I have the top going to a non-zero constant, the bottom shrinking down to 0, there is only one way this is going to happen. The whole thing blows up. In this case, a negative infinity, but if you want to say plus or minus, I'm not going to care. I understand our tools are limited, and finding out which infinity is not the goal right now. It's an infinity right away. I don't have to do a thing. Limit, I did my work. It's in the form. Limit does not exist. If you want to factor this, top one goes to x plus 1, x minus 1. Bottom one, I can factor out an x. And then I have x squared minus 1, which is going to be the same. I'm doing all this work. I'm not getting rid of the problem. The form tells me I will never get rid of the problem. There's a vertical asymptote. It's going to blow up to infinity. The form already tells me all of that. Why would I go through all the factoring work when it's not going to get me anywhere? It's silly. It's all silliness. The form, ideally, tells me everything I need to know. Now, if the form was 0/0, then there is a chance that the bottom problem could feature at the top. There's a chance they could cancel. I need to go explore that. But if the form isn't 0/0, why would I care to do any more work? Back it up. Oh, so close. My undo can only go so far. Don't want to see any of that nonsense. I don't need it. If you want to be busy and make work for yourself, go nuts. I don't need it. I hope for the best, but the 0/0 indeterminate forms tell me to now go dig in the function. Anything else, and I'm good to go. I'm looking for the path of least resistance here. Why make work for myself? But There's a requirement of some understanding. First of all, what we mean by the form, how to use it, what we're saying and what we're not saying. People don't understand what we're saying, and more importantly, what we're not saying. But if you do understand what we're trying to do and what this can tell you, it's really extremely simple. Well, you hope for a form that's not indeterminate, right? Then you're golden. But if you get an indeterminate form, at least you know, okay, let's go dig in the function and see what we can come up with. Oops. So not all secrets are revealed, but I still hope for the best. And honestly, in 2 out of the 3 cases, it's going to be extremely straightforward. Now, there are exceptions, but let's just do this one question. I'll do 18. 18 is over there. Limit x goes to -1. Finite, whoopsie. Finite limit. What's the limit? X squared minus 1. What's the function? X squared plus 1. What do I do first? Nothing. I do nothing. I wait for the instructor to tell me. Well, eventually you have to. You have to, when faced with a question, know what are my options? What do I try first? When that doesn't work, what do I do? And so on. I can totally go to the form. Yeah, absolutely. I plug it into the top, I get 0. Right? -1 squared is 1 minus 1, 0. I plug it into the bottom. -1 squared is a 1. Plus 1 is a 2. And now I'm laughing. Because anything with a numerator and denominator that has individually this kind of behavior is going to go to 0. There is no other way. The denominator is not keeping up with the shrinking down of the numerator. It's doing its own thing. It's saying, I'm off to 2. You do whatever you want. The numerator says, sweet, I will shrink this whole thing down. And no one will stop me. Now, you could have just plugged in a -1. You get a y value. And because it's a rational function, wherever it's defined, it's continuous, everything's good. You'll get a 0. But the form does that anyway. So there's no real need for it. It's really up to you. I don't care. The form is technically overkill when the function is continuous, but it's not going to give me different information. So there's no downside, really. There's no downside to the form. Apart from technicalities, which we have to watch out for. I do have to emphasize this. Now we're getting into the technicalities. There aren't many. That's the good news. But there are some. That is the bad news. Even at this basic level, there are some technicalities that we very easily forget. Whoops, no, that's not at all what I'm doing here. Where's my page here? Nope, that's not it either. Oh, it's up there. There we go. We do forget this. There is this requirement that for this limit behavior question to even make sense to be asked, we need this. We need f, we need the function to be defined around my x value in question. Now, if I'm dealing with a rational function, then I know, or a polynomial, I know everything's good anyway. I don't need to really worry about whether or not the function is continuous apart from its possible vertical asymptote, right? Because this is essentially built on my basic function. I know if I stay away from the vertical asymptote, it's a one-piece function, right? I jump over that, sure. But apart from that, there are no issues with this function. They're sort of, it's very close to polynomials. Or if I have a polynomial, I know there's no issue. So I very quickly, very easily get encouraged by way of my examples to forget this box. And for the most part, I'm safe to do that because the functions are very simple functions. But what are our basic functions so far? It's in my head. It's the library. I have them. I have all my basic polynomials. Great. No problem at all. I have my basic rational function. Sure. Apart from a vertical asymptote, which the 0 over 0 form is going to point out. No problem. But I have other functions, like the square root function, which does present a teeny tiny problem. Teeny. I just need to be aware of it. So, and it's really only for our purposes. I'm trying to think. It's really only the square root function, except if it's some weird made-up function, which we'll see later. Okay, let's have a look at this guy. What would you say is that answer to that limit question? No, it's a safe space. You can say whatever you want. What would you say? You get this pop quiz right now. You have 2 seconds to respond. Of course, you're going to say 0. Everyone wants to say 0. However, unless I keep in mind, let's say it like this, unless I keep in mind what this limit is really saying, I'm going to give the wrong answer. This is asking for the behavior, of course, a very simple function, it's in my library, of my square root function as x, I'll write it out, gets closer to 0, I'll say it like this, from anywhere around 0. It's the same as this. I need to be in my original behavior question. I need to be coming at the x value from anywhere. But this function and its graph isn't defined anywhere. It's only defined on x greater than or equal to 0. So in this special case, it's very special, it's very specific, where I am interested in what happens at 0, I want to be coming towards 0 from anywhere and ask, how does the graph behave? Now this question doesn't make sense because there is no graph here to get closer to 0. I can't travel along anything on the left side because there is nothing there. It is a technicality. It's a feature of this square root function only being defined on half the x values. And for that reason, because of the definition of the limit that we are hiding a little bit, this does not exist. Because the question is not fitting the function. The question doesn't make sense. However, if I ask for the behavior as x goes to 1 of the square root function, totally fine. Let's put 1 up there to exaggerate. I can travel towards that point or that x value from either direction, no problem at all. 1, it exists. Nothing is strange. It's only because the square root function has this endpoint that the original limit question didn't really think about that. It thought about polynomials and rational functions and nice things that sort of has almost all x values, the function almost defined for almost all x values. I always have a window around the x value. I can approach from either side. The question makes sense. Everyone's happy. Now we look at this more special square root function that has an endpoint. And now the question doesn't make sense, unfortunately. Totally a technicality. You might sit there right now and think, but it should be 0. This is silly. And I totally agree, it is quite silly, but technically doesn't exist. However, this is a basic function. The answer shouldn't be doesn't exist. I accept that it is, but there's behavior that is predictable, stable. I want to say more about what happens at 0. Why do I restrict myself to looking around 0? Why don't I just look at coming towards 0 where there is a graph for the question to make sense? Sure, there's no graph on the left, but who cares? I have a graph on the right. I can come towards 0 from that side. And because of this reason, they very quickly realized that, okay, this original limit question, this limit is a two-sided limit. It's a behavior from either side. But that's not always an appropriate question to ask. We want to say more in the cases where there is something to say by just restricting ourselves to only looking from one side. If there is no other side, then let's not care about that. Let's care about the side where we have a graph and change this question just a little bit. So let's do that. There's obviously a nice behavior there. Let's just change the question to allow us to do that. We can ask for the behavior of, well, it doesn't matter what the function is, as x gets closer to some c value, could be 0, could be anything. Now there are two cases. I might want to ask, I want to get closer to c just from the right. And then what we're going to do is we're going to let x approach c. We're going to put a little plus there to indicate that I'm not coming towards c from around c. I don't care if the function's defined around it. I'm only interested on the right side. And of course, then I can ask about the left side as well. So I'm just doing half of the requirement. And I'll put a little minus sign there at the top to indicate that I might be coming from the left side. Now the limit as x approaches 0 from the right, we'll call that a one-sided limit for obvious reasons. Look at my function again. Look at the graph. Now the requirement is I'm only getting closer from the right side. I don't care about the left side of 0. Doesn't exist as far as I'm concerned. There's a graph, stable behavior. It's heading towards the y value that's there anyway. For this, it is 0 and it exists. So it wasn't a bad question to ask. It was just not the technically correct question to ask. If there's no graph, the function is not defined on that whole side of the x value that I'm interested in, I just have to technically change the question to focus on only that side. I'm still looking at behavior. Everything is the same, but this little plus tells me restrict your view to the right side. Or the little minus, restrict your view to the left side. Because that is what makes sense for this function and this x value in question. Okay, so let me just note something else, that I could still ask, I don't have to have a problem on one side. I could still take the limit x approaches 2 from the left of x squared plus 3x plus 1. Now, I just randomly made up that quadratic function. I don't know what that looks like. Maybe over here somewhere. I don't know. Doesn't matter. If it's defined everywhere, then restricting myself to just one side doesn't matter at all. There happens to be a right side I might want to look at. This question says, no, ignore the right side. But it doesn't change how I approach this limit. It's still the same approach. The one-sided limit just allows me, oops, the one-sided limit just allows me to ask the behavior question when the original version, the original question isn't appropriate for the graph and where it's defined. If it's appropriate, but I cut off half of it, nothing is changing the answer. The behavior is the same. Whether I just come in from the left or whether I sort of narrow in on the function, hone in on the function, hone in on the point from both sides, the behavior is predicting the same thing. So in this case, it's the same as plugging it in because it's a polynomial. 4, 10, 11 exists. So the question isn't changed. It's just being made more appropriate for certain functions that have only half the x values available to ask a behavior question. And for our purposes, this is luckily pretty much the only, well, the only technicality really is the square root. All our other basic functions will be, okay, it's not entirely true. For now, will be defined for most of the x values. But when the graph is sort of only half a graph, then I kind of have to look only from that side because it doesn't make sense to even ask about the other side. There is no other side to explore behavior. How do we feel about this? Let me just double check. It was a little hand wavy, but I've never found the change to a one-sided limit to be a very big adjustment. I just need to know it's a slight tightening of the question when it's appropriate. How do we feel about that? Okay, let me just double check what I need to do here. We still have tomorrow, so I don't really want to do too much. Well, we could just do problems tomorrow as well, right? Where am I now? Square root function doesn't exist. We've done that. Great, awesome. Yeah, there's still some stuff. There's still some stuff to do tomorrow. Don't worry about that. Okay. Now, this one-sided limit question now allows us to be a little bit more specific in some cases. We'll just end with this kind of example. Let's look at limit x approaches. I don't have to do 0, but I'll stick to my basic function, 1 over x. Now, remember what this looks like, right? You have to know this very well because it's a basic function. I'm not even transforming it or anything. I have a vertical asymptote at 1. Not 1. I have one vertical asymptote. It's sitting at 0. If I ask this limit question, notice there's nothing with the 0. This is a two-sided limit. Two-sided limit, right? I have to approach 0 from either side. I can do that. I can. The function is defined around 0. Remember, I never care about what is happening at the x value. I have y values around 0. No problem at all. I can explore and investigate the behavior. And the behavior says I am blowing up in terms of the size of my y value. Doesn't exist. Does not exist. And I can't really say an infinity because the behavior on either side is different. If I come at 0 from the right, the y value is blowing up positive. So let's write that in our limit language. I'm approaching 0 from the right. Of my function. Then I can say it's infinity. It's positive infinity. Yes, it still doesn't exist because infinity is not a number, but at least I'm able to say, in addition to not existing, I can say it blows up positive. And I can say, if I approach 0 from the left, it's going to blow up in size, but negative. Yes, still doesn't exist. Fine. But I'm able to say how it behaves. So in situations like this, where the behavior is not the same on each side, I really, for the two-sided limit, can't say anything. I can't say plus or minus infinity because that only meant I don't know which one it is. It's one of them. I just don't know which one. And I don't care about figuring it out. That's what we did. Was there an example here somewhere? Here. It was, well, okay, that's not true. Bad example. We didn't know what to do here at this stage. When I have behavior, we'll come back to that one in a second. When I have behavior, I know it's blowing up in size, but I don't know which one it is. We didn't know what to do at that stage, but we wanted to say more because we knew it was infinity of some kind. The two-sided limit really can't say anymore, even though it wants to. We just didn't know what to do at that stage. We understood it didn't exist. We wanted to say more. We didn't know what to do. But when we have the one-sided limits, we can now be more specific. We just couldn't do it at that stage. So we need to go back. Where is this one? This one? Nope, not that one. This one. We really can't say any of this, unfortunately. So let's just redo that one. X plus 2, x minus 2. Example. Limit x. Now, x goes to 2, right? X plus 2, x minus 2. Now, I don't want to go through a whole song and dance here about the transformations. What we could do is instead say, let's just from the start look at what happens when I approach 2 from the right, what happens when I approach 2 from the left, to see a little bit better, multitasking, to see a little bit better what's happening here. Same function. But let's just from the start split up the sides. Because I suspect, maybe I'm not sure, I suspect something like this is happening. And if you do the transformations, you'll see it is. But I don't know I think there's different behavior on either side. So this one, I really can say nothing. But if I explore by way of the one-sided limits, maybe I can do a little bit, right? So let's, now of course I am assuming that I don't want to spend the time to do the transformations. If I have the graph, of course I can read it off the graph, super easy. I don't know what the graph looks like, I just want to know the behavior, okay? So I don't have that crutch to lean on. What is the form of this first one? Well, if x gets closer to 2, then x plus 2 is getting closer to 4. No question. What in the question would indicate we have to test which side it's limited to? That's a good question. I know because I've seen it before. Really, whenever I have a single power of this, I need to be careful. If I have a squared, then it doesn't matter which side I'm going to, it's always positive. Let me just come back after I've done this bit. It's a matter of experience, really. If I have a single factor that creates the problem, I may need to watch out. That's now assuming I want the specific answer in addition to does not exist, right? The question might be happy with it does not exist and move on with your life. If I now really want to know what is happening and be sure of it, I can always, as a failsafe, do the two sides, even if the behavior is the same. I can always do the two sides. Let's just see it. We just need to see some examples first. Okay, so let me just finish this one. Tomorrow, that discussion is going to continue with looking at two sides separately instead of one. There are more examples. When we have all the examples, it'll feel better. First example is always a little iffy. Let's just finish this. If x gets closer to 2, regardless of which side, x plus 2 is going to get closer to 4. Done. If x gets closer to 2, I know x minus 2 is getting closer to 0. But if x is always on the right of 2, x is always a little more, like 2.1, 2.01, 2.001. If I then subtract 2 from whatever that x value is, I'll get a little positive number. It is still going towards 0, but it's always positive. And I can use that same notation to keep track of that. 4 is always positive, so I didn't care. So all the pieces here, even though I know it's an infinity, all the pieces are positive, so positive infinity. If I look at the second one, this is where people struggle with this, keeping track of the pieces. And I will say later on we will come up with a method to lay it out and structure it better so you can keep track of it better. But for now, it's unfortunately all we have. So when x gets close to 2, x plus 2 is still going to go to 4, no problem. When x gets close to 2, the denominator still wants to go to 0, but now in a more specific way. X is always to the left of 2. So 1.9, 1.99, 1.999. Then minus 2 is going to give me a little negative number. The direction that those numbers are going is getting closer to 0, but they're always negative. Positive number, negative infinity. Which is why I said something similar is happening here to this. See, on either side, it's a different infinity. It's my vertical asymptote, which is why the two-sided behavior is not consistent, and I can't say anything. They're not matching. But if I had, I know I'm going over time, but we need to paint the picture as clearly as possible. If I had something like this, then on either side, I'll write it out. You can convince yourself. This guy is always going to be positive. this guy, if I approach from the other side, because of the square, it's also positive. That behavior is the same, and then I can say, okay, there is consistency between the two. They behave the same way regardless of which side I'm coming towards to. And I can then merge them into a two-sided limit because the behavior is the same. They agree with each other. But in many cases, they don't agree with each other. Different things are happening on different sides. Then the two-sided limit is completely screwed and can't say a thing. And the only way for me to say more is to isolate the sides and show, oh, no, they're different. Okay, fine. I can't merge these into a two-sided limit. I can still explain the behavior, but because the sides are different, I have to do them individually. Even if I'm not sure, I do the sides differently, and I see, oh, they're the same from either side. Okay, now let's merge them into the two-sided limit. Answer. There's no downside to looking at the sides separately. I might create more work for myself when I don't need to, but I can always be safe and do that if I'm not sure. Now, with experience, you start to see, well, okay, if I have a square here, it really negates any positive negative differences because it's always going to make it positive and so on. But as a failsafe, I can always look at the two sides separately. Now, to be fair, we have to look at more examples to really emphasize this. When do the two-sided limit, when do the two-sided limit results agree with the two one-sided limit results? So just a few more examples, and it will hopefully demystify this if you're not sure. This was a little bit rushed. I just wanted to finish the story here, but more examples will show the link between the one-sided limits and the two-sided limits because there's a very strong link. It's the same question. It's just a matter of how does limiting myself to one side only allow me to say different things or confirm the two-sided case and so on. They're not different questions. They're just one is sometimes a little safer than the other, and I need to do the one-sided limits to be more specific and to be able to say as much as I can. All right. How do we feel about limits and one-sided limits? Let me get our schedule open to see where we're at. Yeah, I want to look at both. I'm going to look at both. Okay, let's zoom in here for our schedule. Get away from me again. Okay, so we are second part of finite limits. Now we've started, these have overlaps. I can't get the hour perfect. We've started the idea of one-sided limits. We'll continue that on Monday. So I would say wait on one-sided limits if you want until we've maybe covered all of our examples. But all other limits are good to go. No, these are limits. Change. There's our limits. So where are we? Auto limits, infinite limits. We've technically had the opportunity to do 2.1 already, but if you haven't yet, certainly do that. 2.2, all the finite limits should be good to go now. Hopefully there's enough variety there. Yeah, maybe leave out these absolute values just a little bit. They are tricky and Monday would help for them. just normal functions, square roots, rational functions, rational functions, yeah, square roots, the common functions. And then 2.3, one-sided limits. You can, if you see something familiar in terms of the examples that we did, certainly like the square root ones, you can go for it if you have nothing else to do. Uh, but we may want to just be sure, maybe wait a little bit, but technically you can handle all of these. We haven't done a lot of examples, so it's totally up to you. If you've caught up with everything, give it a shot, see how you feel, but you're also totally fine. Check the schedule again. So the next week, so rates of change will be where the midterm one stops. So Tuesday, we are done with the midterm material. Even though we are going to slowly continue, we kind of have to. The midterm will stop at topic 3. And then Friday we'll have a Q&A session in preparation for the midterm if you need it. Any questions in addition to, and of course many people take advantage of it as you go and you do a problem and you're not sure, you're not confident, let me know. Check them. I understand there aren't any answers for our problem book questions. um, Match it with your exercises. It should be okay for the most part, but right. Until next time, enjoy the weekend. Sunny.